Alrighty. So we'll go ahead and get started on this webinar right now, which is about asynchronous state machines and how they compare to microcontrollers. And hopefully you guys are as excited about this subject as I am. And Silego is, in fact, already shipping a lot of asynchronous state machines, primarily in what we call our 5th generation PAK family. You can find those in a part number if you download our software, our GPAK designer software, which is available for free off of our website at www.silego.com. You can find the devices with an asynchronous state machine in them by one of the device numbers is SLG 46531. That's one that's currently available, and we're going to have more that are available here shortly. Okay, so let's first of all, let's talk about what's involved in talking about the difference between asynchronous state machines and MCUs. Now, the first term I use here is a finite state machine. And the proper definition of a finite state machine is a state machine is a device that can be in one of a number of states based on its previous inputs and on the present values of its inputs. So it's an incredibly large definition encompassing just about anything that does any type of logic. So you've got input states, you've got output states, and the present state is determined by those inputs from that are coming in, as well as the present values of the inputs to determine what the next output state is going to be. A microcontroller is a specialized state machine. Now, so it isn't really technically accurate to compare finite state machines with MCUs. Now, there is practical definitions in the world of engineering. So I'm trying to give the precise definitions to start with, and then we'll talk about what people actually mean by these things. If you think about a microcontroller, it executes a line of code that's sort of like a state. It has it decides where to go with the next state, determine on what the values of that present state are, and any new inputs that come in, and then it goes with the program counter to the next line of code, which could be considered another state. So in essence, a microcontroller is the specialized state machine. But that's not really what people mean in a practical sense, which we'll get into in a minute. Now, Silego's finite state machine is another specialized type of state machine, and we call it an asynchronous state machine. And we'll talk about more about what that is in a little bit as well. So let's talk about what people actually mean when they say the difference between a finite state machine and an MCU. A finite state machine is a system with a defined number of states. So quite literally, when an engineer gets up on a whiteboard and says, okay, this is what I want my system to do, and they draw a bunch of circles, and those circles represent conditions that their product can be in. For example, you hit a button, the next state is the on state. As part of that on state, you might want to go check and make sure all your power supplies are up correctly. You might want to make sure that the temperature is okay, in which case then you might realize your battery's low, so you enter a battery charging state. And your system can only be in one state at the same time, at any moment in time. It can't be in multiple states. You can't be doing multiple stuff within the state machine. Now, I'm talking about what people practically mean, not all of the corner case conditions where you could say, well, I could design state machines that would do other things. So usually what people are referring to are control-oriented states when they talk about finite state machines. So things like on, off, wait, turn something else on, vibrate a haptic sensor, etc. And they generally are talking about the control of that being logic high or logic low signals, as opposed to code or command level commands as you would have associated with a microcontroller. Now, in a hardware state machines, we use the flip-flops to hold a current state. So you actually physically have a couple of gates that are cross-coupled, that form a flip-flop, and that flip-flop is a latch that ends up holding the current state you're in. Now, you can have multiple outputs from that current state that can go and control LEDs or whatever you want, but the fundamental device that we hold that state with is a flip-flop. The total number of states is limited by the number of flip-flops in the interconnection, in the hardware sense. Now, on the software side, we also talk about finite state machines that you can actually build on top of an MCU. And that's not really what we're going to discuss today. What we're discussing today are finite state machines in hardware at the lowest level, you know, at a transistor level. We're not discussing how you would build a state machine. Now, just for a moment, I'll discuss that briefly. When people talk about a finite state machine in software, they're normally talking about code that only can go to a number of different conditions, and none of those conditions can have while commands in or other commands that are a little bit dangerous to use in an embedded control application, such that you could get into an infinite loop. You know, you could say, okay, while write a while command, and you're looking for some event happening in I squared C. If that event never comes in, you could actually wind up in an infinite loop, and that's a big no-no in terms of embedded design. You can't have your machine obviously just go off into an infinite loop and not be able to respond to anything. So some software engineers write code that is dedicated just to never be able to get into one of these conditions, or use any commands that are associated with those conditions, and only have a fixed number of those conditions that kind of rotates through these commands over time. Once again, that's not going to be the conversation we're having today. What we're having today is flip-flops that are actually physically down on silicon with interconnects that have a defined number of states, and that interconnect can connect those states up into a logical patterns to allow you to do to build these state machines that allow you to control devices. So the problem with finite state machines is this: when you start to get above 8 states, 10 states, 12 states, and you start to get into a lot of states in complex equipment, designing a really good finite state machine is pretty dang tough. It gets really, really hard. And so years and years ago, when microcontrollers came along and allowed people to solve problems, you know, one little micro step at a time, microcontrollers came to dominate the world. Even though FSMs and asynchronous state machines have a lot of benefits in terms of power, efficiency, and these types of things. The presentation here isn't so much what's better or what's worse. It's more of an introduction to, you know, what do asynchronous state machines excel at, and what do microcontrollers excel at, and how can they play nicely and offer a designer the best of both worlds. So let's talk about microcontrollers for a moment. As I said earlier, a microcontroller is a form of a state machine, and I like to jokingly refer them as the infinite, instead of a finite state machine, an infinite state machine. Basically, when you think about a microcontroller, very few people even think about states. They just start, you know, they write lines of code up, and if you were to implement those lines of code in a state machine, and it turned out to be 1,000 states, nobody would think twice about it. And nobody, you know, if you ask your software engineer after they finished their firmware and ask them how many states they had used, many of them wouldn't be able to answer that question. And they could only answer it at the highest level in what are their macro states. So a microcontroller is usually used for both control and data processing, whereas finite state, the types of state machines we're talking about generally are emphasized on the control side and not the data processing side. Microcontrollers come with a couple of different architectures. One is the von Neumann architecture, which is generally associated with the CISC architecture. And I could go more into that in detail. It came from Princeton. The roughly developed nearly at the same time was the Harvard architecture, which separates the data memory from the program memory, and is generally associated with RISC type machines, or reduced instruction set computers. The number of states is only limited by the program storage code, and today memory, you know, it gets cheaper every year relative to the total amount of it, and thus programs can be incredibly complex and incredibly deep and incredibly rich. And it's not uncommon. I was looking at one microcontroller just the other day, had 384 bytes of flash program memory, available for it, and that was just unthinkable 15 years ago when I was doing different types of microcontrollers back then. I mean, we were pretty happy if we could put 16K bits, and now in a very large device that sold for multiple dollars. And today you can buy 10, 20, 100x the amount of capability, and this continues to just increase. So the problems with microcontrollers have really never gone away because it's associated with fundamentally with the architecture limitations of microcontrollers. And that's one thing, is what happens when you run out of memory. If you need to store a lot of data and you don't have anywhere to store it anymore, that can create problems. If you are storing program memory and data memory in the same physical memory locations, you can have accidental overwrites, you can have stacks that overflow. You can create infinite loops like we were talking about really, really easily. The response time for microcontrollers, and we'll talk more about that later, can often be very lengthy. You can have a lot of timing issues with microcontrollers. It's very easy to violate the setup and hold times that are associated with reliable designs in microcontrollers. We'll talk more about that later on. And naturally, because these are clock systems, you never get rid of power consumption. Now, microcontroller companies have done an amazing job to reduce the amount of power and use all kinds of sleep and hibernate modes and various ways of turning on and off PLLs and clocks to really get the amount of power consumption wrung out. But nonetheless, microcontroller architecture is not the most efficient architecture for power consumption when you're trying to do relatively simple problems. And then finally, they're expensive compared to finite state machines or asynchronous state machines for doing simpler control type applications. Now, what are the benefits of asynchronous state machines or finite state machines? One is they're more natural. Believe it or not, long before we learned code, when you're a kid and you're growing up and you think about how to solve problems, you think about, well, I'm here, this happens, I'm going to go do something else. And it's kind of how our brains kind of naturally work. So ironically, when a lot of engineers want to describe a problem, they don't start writing code to explain that to their colleagues. They start with a logical diagram and they'll say, okay, I'm in this state, and then if this happens, and they'll point an arrow and draw another circle, and this comes very, very natural. Well, that is kind of naturally how state machines work. And so it's a very intuitive way to design, and I'll show you how later on how Silego takes that intuitiveness and has actually wrapped that in software so that when you actually design with our state machines, it is completely natural. The next thing is finite state machines and asynchronous state machines are extremely power efficient. One of the reasons why is there's less movement of data. There's not generally large buses that are moving data in and out of memory repetitively. Very often there's a single step from whatever logical signal came in, and you want to transition from this state to the next state. That's done in a single sweeping motion. An asynchronous state machine is done in just a few nanoseconds. It would be the equivalent of a single clock cycle in an MCU world, and then you're off and running. They're also extremely reliable. It doesn't mean that you can't design really, really broken state machines. You can. But you can absolutely define a state machine with fixed known states and how those states interact and what the logical level of those states are, so that you don't have any ability to crash. And because every state is known, there's no memory overflows to worry about. There's no infinite loops to worry about or that type of thing with a properly designed state machine. And it's not hard to do that. Finally, one of the benefits of state machines is they can play very, very nicely with MCUs, and we'll see that later on in the presentation. Now, just to kind of explain a little bit of a diagram that would go into the state machine here, Think of, for those of you who are more familiar with the coded world, every one of these arrows pointing, going from one state to the next state, a state being the on condition, and maybe the next state being a vibrate condition, or maybe the next state being a read, read something. Those arrows are like if-then statements in the code world. So if you're in state X and something happens, then go to the next state. That's pretty much what that type of thing means. And what that if something happens is, those are logical gates. Those are signals that come from pins, signals that come from sensors via comparators or A to D converters, that type of thing. And when a particular level of signal is sensed or whatnot, then you transition from one state to the other. So just think about them like if-then statements. Now, what are the benefits of microcontrollers? One, and probably the single largest benefit of a microcontroller, is it's much easier to solve large problems with microcontrollers because it's easy to code. The coding allows you to break down problems one step at a time in manageable chunks so that you can wing through very, very tough problems fairly quickly. Now, this burns a lot of power. It slows everything down, but this is why Moore's law is so important. What we learned in the semiconductor engineers in the semiconductor field almost from its inception was, okay, well, yes, you're going to go slower. Yes, it's going to burn more power. And the answer to that is Moore's law, or let's shrink the geometry of the silicon. And when you shrink the geometry of the silicon and you make smaller transistors, well, those smaller transistors are faster and they're more power efficient. So simply with money, you can buy more speed and you can buy lower power consumption. So you get all of the best of both worlds. You get the easy to code, you shrink your geometries, and you get your speed back and your power consumption back. And if your coded problem gets larger, well, just shrink geometry again and you could get more speed in your parts. So money can solve your problem in the microcontroller world for the most part. Now, that stops being true at a particular level in a particular geometry, where the geometries get so small that the process itself gets leaky and starts burning power consumption. And for certain IoT applications that have very small batteries and things like that, that can start to become a problem in and of itself. Now, the architecture of the microcontroller is quite interesting. It is a very, very simple architecture. You basically are in one state, and you've got two options. You go to the next program line of code, or you go somewhere else. And every state is like that. And there was a lot of reasons that microcontroller companies and architectures took on this, very simplistic architecture. And that's primarily because memory was expensive. Having an 8-bit wide memory was a big deal back in the day. And then we went to 16 and 32 as memories became cheaper. But nonetheless, the bus architectures couldn't be infinitely wide, and so to keep the buses relatively narrow, you didn't want to give a lot of options as to where you go, because anytime you get an option that requires more data, it requires a larger bus width, and that wasn't something they wanted to do on silicon. And so as silicon and geometries have shrunk, they widened it up, and we find new optimizations in terms of how much data we can process. But nonetheless, the architectures stay very, very similar. Now, I've sold hundreds, if not billions, of microcontrollers in my life. And one thing I've noticed about a lot of microcontroller code is it's complete overkill for the application. So there are many, many electronic products that have microcontrollers designed in to sense, a turn on button, turn on a motor, to, run a shaver, turn on a status indication light for the battery consumption, and maybe a little bit of security circuits or safety circuits in case, there's some detection of the case opening or something getting dunked in water where it shouldn't be, et cetera, and being able to do auto shut-off commands. Most microcontrollers can run these types of applications using only 2 to 10% of their entire capability. And as a result, people are overpaying for their solutions. They're paying 25 cents, 30 cents, 50 cents for these microcontrollers, when in reality they could just use a state machine and save money, quite a lot of money. Furthermore, the state machines, being inherently crash proof, are often a more reliable way to run these simple types of applications. If you have a flashlight, for example, and you click the on button and the light turns on, and you click it again and it goes to some blinker mode, and you click it again and it goes to high brightness mode or something like this. These are all things that can be handled very, very easily with the state machine, very power efficiently. We can do pattern generators, we can do ambient light sensors and condition inputs and status the LEDs, and do all of these kinds of things without having all the expense and problems that are associated with an MCU. And we do it, the configuration of this, in a piece of software that is very intuitive and very easy to understand, and can knock these kinds of projects out very, very quickly. Now, that's state machines replacing MCUs for simple applications. Now, there are a lot of applications where you really do need an MCU because you need the data crunching capability of the MCU. But in many of these applications, you will find that our GPAK asynchronous state machines are very cheap, reliable, no crash configurable crash detectors. So MCUs can crash, and there are many standards in the world today, both in Europe, the United States, and Asia, that require a separate chip to be there to monitor the MCU in case it should crash in a mission critical application, let's say a smoke detector or some security sensor, glass break detector, and be able to monitor that MCU to make sure that it's still alive. And if it's not alive, put out some kind of notice, light a yellow LED that says, hey, you know, this device isn't working properly. Perhaps go and reset the MCU, you know, record the time that it crashed, on and on and on. So GPAK MCUs are very cheap, they're reliable, there are no crash configurable crash detectors, they can do reset, statusing, all of this type of stuff. Beautiful MCU backups for times when specs require the company to have a backup to the MCU. Now, I hope you can really get this point, because it's both a subtle point, but for many people, it's really an aha moment about just how powerful GPAK asynchronous state machines can be. It's a beautiful MCU companionship, and by that I mean this. Almost any person has a little bit of schooling and a good math background can become a firmware engineer. And you can start to write code that is reasonable and does what you expect it to do. The difference between a novice or beginning firmware engineer and somebody who makes a lot of bucks in the Silicon Valley in firmware engineering isn't the ability to just make something happen, but it's the ability to make something happen and then cover all of the failure modes that are associated with that particular device. It was very common when I was working in the microcontroller world to see the actual code that drove the device was 10% of the code, and 90% of the code had to do with failure modes. What happened when something didn't work right? You know, what happens if the user came along and yanked out the battery charging cord in the middle of the battery charge? What happened if that you ran out of memory and the stack started overflowing? And what happens if the motor's running and the temperature sensor goes off? How fast do you need to respond to shut that motor down before everything overheats and melts down? And what's the timing associated with that? And most of these problems are all related to interrupts. So in the microcontroller world, we have things we call interrupt service routines. So you have to detect the interrupt, then you got to run over to the specific code that's associated with the interrupt. You got to run that code, then you got to jump back to your main code, and, you know, and all this kind of stuff goes on. And then you have multiple interrupts kind of sort of happening at the same time, and making sure that all of your code throughout all of that time plays nicely with each other. It's a nightmare. It is extremely difficult, and that's why firmware engineers make the big bucks. It's because they have to make sure that under no condition, with all these interrupts happening in all kinds of random orders, that their microcontroller firmware code stays healthy, knows exactly what to do, and always goes to a known condition and never runs into problems where all of a sudden you get in for the loops and all these kinds of things. And all of this needs to be timed out in real time to make sure that your system not only stays crashless, but also meets the requirements of the system to be safe for the customer's usage. That is not easy. So one thing that many embedded firmware engineers have come and done is that they've used the GPAK asynchronous state machines and they butted them up next to microcontrollers to handle a lot of these interrupts. So as these interrupts come in, the state machine can decide in many cases to go handle the interrupt all by itself. You could have, okay, I've overheated here. Okay, I'm going to go shut the motor down, or I'm going to slow it down automatically. And then in a more leisurely pace, you can send that interrupt over to the microcontroller, and the microcontroller already knows, oh, the motor's already slowing down, so you don't have to have some extreme speed, and you can service your interrupts on the microcontroller in a much more calm, rational sort of way, in a much easier way that's guaranteed. So that's just one example, but I could give you 50 more examples in terms of just how GPAKs can work with microcontrollers to not only detect when they crash and things like that and reset them, but also can make your code a lot cleaner and a lot easier in the timing, much better, simply by using a state machine outside of the MCU to go and handle a lot of the easy to use, a lot of the interrupts that might be coming in. For those of you who have actually written microcontroller code, you'll appreciate what I'm talking about. So let's talk briefly about the difference between an asynchronous state machine and a finite state machine. Essentially, the finite state machine is a clock-driven state machine, and the asynchronous state machine is an event-driven state machine. So when you're trying to go from one state to the next state, on a finite state machine, there's a clock that's happening, and that clock is clunking along, and with every clock cycle, you can check what the inputs are and what the previous output states are to determine whether you need to move to a new state. With an asynchronous state machine, you just sit there idle, waiting for an event. And whenever that event happens, the circuit springs to life instantly, I mean within nanoseconds, and decides what to go do and transitions to the new state. It should be intuitively obvious that an asynchronous state machine is a much more power efficient device because there is no clock working. It's not periodically checking anything. It's waiting statically, only leaking current that's associated with its process, which is down in the nanoamps, low nanoamps, single digit nanoamps, waiting for events to decide what to go do. That's the type of thing that we're talking about. We call this our zero static power state machine, or the GPAK asynchronous state machine. So the FSMs periodically use a clock to check for changes in the inputs to determine whether to move to one state or the next. Clocks burn power. Clocks also mitigate timing issues. So nothing comes for free. When things are sitting there statically waiting for an event, there's a lot of different problems that can possibly occur in that particular type of architecture. The reason people use clocks isn't because they're stupid, it's because they want to mitigate timing issues, even though those clocks have a power penalty associated with them. The way we get out of that is this. The GPAK ASM uses the event, and using the event, then we determine where we're going to go. But in using events, we generate the possibility for what we call hazard conditions. That's where a signal takes two different paths within our chip and can result in unwanted pulses and this type of thing, or metastability issues. Metastability being, well, I'll talk about that in a moment, need to be considered. But so you can actually have logical problems with this particular type of architecture. So what we've done is we've built an asynchronous state machine that eliminates any hazard condition, and we'll explain how we do that in a moment, and also mitigates the metastability. And notice I use the word mitigates. It's impossible in a digital system to totally eliminate metastability because it's a statistical process, but you can mitigate it to such a level that statistically it should never happen. And that's what we've done. And we've tried these devices out to trillions and trillions of decisions and without any kind of failure. So Let's talk about metastability. Metastability happens when two signals appear at exactly the same time going on to inputs and violate timing and hold setup times for that particular device. So if a signal came in, for example, in this particular circuit on R and S, which is a RS flip-flop, the signals, you'll notice that this circuit is cross-coupled. And so the output of the NOR gate that's associated with the top signal R is connected to the input of the NOR gate associated with S, and which is then fed back into the input of the other one. And so you can see that there's two feedback loops here, and if two signals come in exactly at the same time, you could get a condition, what we call metastable, where these signals are chasing each other around the loop, trying to one signal to catch up to the other signal, with the hope that once one signal does, it goes to a known latch condition and it stops doing that behavior instead of oscillating. Theoretically, this condition could go on for some arbitrary time. Now, statistically, with a small enough geometry, fast enough signals and that kind of thing, we can say statistically that, you know, this isn't ever going to happen in any kind of real world. However, you can also design them bad enough where indeed they could happen quite often. There are ways to eliminate metastability. One is by using two-stage flip-flops and then use an arbiter, basically, which decides which signal has priority. And we can statistically eliminate any metastability or hazard / race condition issues. And that's what we've done. And so our asynchronous state machines can be used quite safely and still have all the benefits of low power. So I want to talk about one of the ways we eliminate these hazard conditions as well. So there's two traditional architectures within the asynchronous state machine. One of them is when you transition from one state to the next state, the state that you're headed to, the next state, in this case S1, sends back an acknowledged state to the first state that says, okay, while you're transitioning, nothing's going to happen and we're not going to accept any new inputs until that acknowledged signal comes back from the state that I entered. And after that acknowledged signal comes back, then we allow state one to go off and do something else and detect new inputs and go to the next state. In this way, the acknowledged signal is equivalent to a clock signal in a clock system. Basically, it's the time period where nothing's allowed to happen other than what just happened. And in this case, and by doing so, we're able to prevent conditions where I can be in one state and accidentally jump to two different states. That would be a disaster in a finite state machine or an asynchronous state machine if you had the ability to be in one state. Two logical signals come in at exactly the same time, and those logical signals are indicating to go to two different states. We need to only ever go to one state, and thus one of the ways to prevent that is to use acknowledged signals and arbitration to decide which one has higher priority. That's not the architecture we use. In our chip, we use what we call the time of flight. Essentially, when we decide to go from one state to the next state, we have an arbiter that says which one has priority. We start to send the signals out. We have actually two paths. One path is longer than the other path. And so the real path is the short one, and then we say the done path, which is longer. And so we always know by design that our done path is going to come in after our main signal path. And in this manner, we always have a time period set up by the time of flight. We always have a time period by which we'll have enough time to arbitrate whether or not we should have gone to S1 or, for example, a different state, S2. I hope that's clear. And what's beautiful about that is these times of flight are independent of process voltage and temperature. So we're able to guarantee these things. For example, if we're at 5 volts and the time of flight is 15, probably should be more like 15 nanoseconds rather than 15 microseconds, but nonetheless, if the time of flight is 15 microseconds from state 0 to state 1, and then our done signal has been designed to be 25% longer or 20 microseconds, we can always guarantee that we're going to have enough time for arbitration. Now, let's say that we've lowered the VDD on our chip to 1.8 volts such that the actual time through all of the transistors and traces is 30 microseconds. Well, the same thing will happen on our done signal because it's a percentage of the real signal. Therefore, our timing is always met. This means that no matter how our fab builds our chips, we're never going to end up with a condition where we don't meet setup and hold times. No matter what temperature the device is at, we'll always meet our setup and hold times. No matter what our voltage at, we'll always meet our setup and hold times. This is very different than most microcontrollers. Most microcontrollers, their time setup and hold times are set very, very precisely, and that's why they have to use regulated supplies, and they're allowed to have 1.8 volt plus or minus 5% or something like that, and you have to provide an LDO or a DC to DC converter to provide exactly that voltage. And then many of them have limited temperature ranges and things like that. Well, that is not true with our asynchronous state machines. You could hook these up to a lithium-ion battery directly that charges up at 4.3 volts and discharges all the way down to 2.3 volts, and without regulating anything in our chip, that our asynchronous state machine will not crash, won't have any kind of timing problems, will be completely stable that entire way, and you could even jerk that power supply up and down. Incredibly robust piece of circuitry that is just the nature and architecture of the asynchronous state machine. Oh, don't want to fail me. The regulator, not requiring a regulator, is another way we save power. If we have to require a regulator, I mean, the world's lowest power LDOs, they're working in a microamp, and they're very, very slow, and they're quite noisy. More expensive one, more stable ones, and ones with less noise are running up at 10 microamps, 30 microamps of all unnecessary power consumption. All that is done away with when you use our asynchronous state machine, because you're not having to rely on a constant voltage supply to maintain your timing and hold setup times. Now, the next major point we're trying to make here is zero latency. Now, obviously, it's not truly zero latency, but it's so much faster than microcontrollers. We just, in the marketing world say, hey, if you're 100 times faster than your competition, well, we'll just go to the extreme and call that zero. The truth is, interrupt latency in our ASM can be as fast as 50 nanoseconds, and you compare that at even fast microcontrollers at 5 to 10 microseconds, and I'll explain this in a moment in more detail right now. So let's talk about what an interrupt is. An interrupt can happen, like a sensor goes off and detects a hot event and sends a signal over to the microcontroller. That microcontroller might be in a very, very low power mode. Let's say that only a 32 kilohertz clock is running. It intercepts that signal at the next clock edge. So by definition, you've already wasted 33 microseconds if you're in that lower power mode. And then you can start to go, okay, wake up the interrupt service, change the clock speed, blah, 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 and handle all the code that's associated with the interrupt service routine. And shut back down, and so 50 microseconds later, you've processed that interrupt, done whatever you need to do, and shut back down. Our asynchronous state machine, because it's event-driven, as second it sees that event, it pops into action, 50 nanoseconds, 30 nanoseconds, these kinds of things. We don't need any oscillator to change, to do anything. We're not changing the speed on anything. We're not having to load code from an interrupt service routine. We're not having to access buses or anything like that. It's just, if you see this event, direct hardware, go to the state that handles that particular event, whatever that alarm is, shut down the motor, turn on the sprinklers, do whatever it is, bam, all handled by logic, and this thing goes back to sleep. There is no clock. That is zero interrupt latency. In fact, we try to make the latency low enough where the actual embedded designer doesn't even think about the latency. They just look at it, wow, 50 nanoseconds, that's so fast, I'm not even used to dealing with that. It doesn't even go into my timing diagram hardly. That's really our goal with doing that. So I've kind of broken it out in this slide and talked about what does an MCU do. Well, if an interrupt comes in, that interrupt is detected on the next clock cycle. Once again, I'm assuming that we're in a low power mode. Next clock cycle, you start the interrupt service routine processing. You start the beginning of that. Generally, you have to adjust the clock speed up, so you're going to burn a bunch of power here. You know, to be able to. Generally, it takes 1 or 2 clock cycles for those clocks to come up, and then you start clocking pretty quickly. And once you go into, you know, 8, 30, 40, 50 megahertz MCU, you can process that code pretty fast. Once you're done processing it, you go back to sleep mode. Compare that with a GPAK ASM. One is we will detect the interrupt virtually the nanosecond that it happens. We'll process that interrupt generally in less than 10 nanoseconds. We'd never have to adjust a clock speed. We'll complete the process, and we go back to zero static power mode, all within 50 nanoseconds. That is the unbelievable power savings of an ASM for control type applications, and why you can save an enormous amount of power while it greatly simplifies your code from interrupts. And actually can make your system a lot safer, because if one of these signals is quite dangerous, you can take action on it in incredibly fast speeds. This is the beauty of GPAK's ASMs. And just to kind of illustrate, here is a slide from Renesas. It's a public slide. Not really trying to say much about the product line, but you can see, you know, down here they've got their various real-time applications: glass break, smoke detect sensor, healthcare applications, remote controllers, UARTs, this type of thing. And you can see how they put a lot of effort into, you know, how are they going to handle this fast wake up is good, but it doesn't always have an effect. They're trying to call fast wake up 30 microseconds. I just told you 50 nanoseconds for us. So not quite 1,000 times faster for the pack. That's why, I mean, architecturally, we're orders of magnitude better than microcontrollers in handling interrupts. Because an interrupt basically is our signal. It's not something that happens in addition to our signal. It is what we work on. So now I want to show you the, let me see here if I can bounce out of here and bounce into here. I wanted to show you new share. Here we go. I want to show you our particular. Okay, hold on. I need to. Share this screen. Hopefully you're seeing a screen that is black in the center and it's got thing. I want a little box here with VDD and temperature on it. I'm just going to hit OK, and I'm going to turn on our ASM. For those of you who are unfamiliar with the PAK software, it's almost like a schematic capture type of software. You know, you can add comparators and that type of thing, and you can turn those comparators on. Hold on, I've got. There, I turned that comparator on. But this is the asynchronous state machine, and I'll zoom in on it a little bit. This is what you're going to see. And when I want to define what that is, I can go into the ASM editor, and I can show all the states that are associated with it. And I can name those states. For example, maybe this is my initial condition or on state. I've talked about, you know, maybe your battery check state. You have some other state. I don't know, vibrate, for lack of a better word. And you could start to build your state machine. And what you can do is you can set the links with the arrows. And I'm going to try to zoom in here a little bit better so you can see what's going on. I'll just do an arrow there and an arrow there, and you can draw crazy stuff. And every one of these arrows, remember, is an if-then statement. So if I'm in on and I want to go to state 7, something's going to have to happen here, and this will become a logical input in another screen that I'll show you in a moment. So I'm just going to make a bunch of arrows, and I'm not promising that this is a good state machine design. Hopefully I don't have any states where things just can't work properly. And one of the fun buttons here is your is the auto route button. I'll show you how that works. But it kind of redraws everything in some kind of weird state diagram. But at any rate, now you go ahead and you build up your logical diagram like this. You hit apply, and then I'm going to close out of that. And you'll notice that all of the states, on state, battery check state, vibrate state, state 3, so 4, 5, and all of these signals, all of those arrows that were the if-then statements that would transition you from one state to the next, they become a logical signal here. And so now what I can do is I can use logic. Like here's a little logic block that I can turn into an AND gate or an OR gate or whatever I want. There's an OR gate. And I can connect that logic to the input of that. So if I'm in the battery check state and I want to go to the on state, whatever happens comes out, whatever signal comes out of that gate is what is going to control that, the ability to transition from battery check to on. Now what I can do also is I can also use a pin and transition from a pin. I can go you know, take pin 3 and whatever, if high goes on pin 3, that signal gets translated over here, and I can transition then from the on state to state 7. Or I can take pin 3 and feed it through some logic here, and I can feed the comparator output to that logic, and I can configure this as an analog input and hook that up to a comparator. So whatever signal is here, I can compare that, you know, let's say with a 900 megahertz signal, and feed that into a logic, and that can control that. Now, each state in the, I'm going to break apart this for a moment. Each state in the ASM can have 8 bits associated with it. So when I'm in battery check state, the ASM output, hopefully you can see that, I'll zoom in. The ASM output will output 8 signals, you know, 1s and 0s, 8 signals that are associated with that battery check. If I go to vibrate state, once again, 8 different signals will come out of here. These signals can be routed around on the die itself. I can take those signals, and I can take a signal and I can put it over to logic. I can take one of those ASM output signals and I can put it and control different states like a normal state machine, where the output of an existing state can control where the next state's going to go. So the output of the ASM can control whether or not I go from state 5 to state 3. Likewise, let's say I want to make some LED controller. I want to say, well, if I'm in a fault state, I want to light a yellow LED. So I can come over here and go, okay, if I'm in a fault state and I'm going to say that fault state is associated with the output out 5 of this ASM, I can go plug that in there. And I can go set the label on that, and I'm going to say that's my yellow LED. And so if I'm in a, you know, state 4, which is a fault state, coming out of that signal can come over here to pin 16 and light an LED. I hope that is easily obvious to you guys. And then I have development boards, development kits, these types of things, demo boards, whatnot. And when you want to go program your device, you just hit the emulator tool. I don't have one hooked up right now. And you can see that we have a design rule checker that says I've got all kinds of problems. But at any rate, the point isn't really to show that. But nonetheless, within the emulator tool, you click on that, you can simply take whatever you design here, it sweeps it over and immediately programs it into the non-volatile memory within one of our 5th generation PAK chips. Now we're also coming out with our 6th generation PAK, which will have a richer asynchronous state machine in it, and have up to 12 states and far more logic associated with it. And instead of just having 20 pins, it's going to have up to 32 pins. We'll also have smaller versions of that one as well. Now, you can also use I2C. You can write to a particular I2C register, and those I2C registers can also be used as inputs. You can also take the I²C, and you can actually look at all of the outputs of the ASM and actually read that back through I²C as well. Okay, now let's see if I can get back to my other screen. Hopefully you're seeing a presentation screen. And so you can wire these things all up, and you take inputs and outputs from all over the place, just like you would in any schematic capture tool. And there you go. You've made a very, very simple design. We have lots of examples on our website. So bottom line, GPAK ASMs are easy to use, low cost, ultra reliable. The three main points to come away with is they have zero static power, zero latency, zero code. And one of the beautiful things about having zero code associated with it and being able to design like we were today is it's not uncommon for firmware engineers to have thousands of lines of code that need to be qualified. And then they find out, wow, you know, in the middle of this, they've got a time meter setup problem in one of their interrupts, and they're looking at a 4-month delay in their project because they got to go recertify all of their code again. Well, GPAK ASMs, once again, no code, small little design change, just change a delay on something, just change the state on something without any code whatsoever. You can get back to back on schedule. It makes it very, very easy without having to go through massive requal efforts on the firmware side of the particular project. Hardware engineers generally love having this capability of being able to configurably change the timing, the turn on of power supplies, the sequencing kinds of issues, and do that all code-free using the Silego development environment. So the configuration software is available at www.silego.com. And a couple of part numbers that we have on this is the SLG 46531 and the SLG 46880, which will be available here in the next couple of months for our 6th generation pack. Okay, if anybody's got any questions or anything, now would be a great time. I finished off the lesson for today, the webinar, and love to hear from any of you. Okay, with no further questions, I thank you guys all for your time, and good luck on all your designing. Take care. Bye.